Welcome back. This is the lecture on time series and sequential data. Particular sequential data are an extremely important topic. So there's a difference between these two things, but they're also connected. Here's an example of time series modeling. I have to predict the total energy consumption of a city for tomorrow based on certain inputs like weather forecast. So they might predict temperature, precipitation, wind. Maybe a label is if tomorrow is a working day, a holiday, and there are probably a few other features. But of course, this prediction, we could do it based on just these features, but maybe also the energy consumption of today is important for this prediction because maybe tomorrow is the same as today. And maybe also from yesterday. So maybe you want to see a trend from yesterday to today, and the trend might continue. It can become even more complex. So if you want to predict several days in the future, then my prediction for tomorrow might become an input to the model. So I iterate the model. And is this a good idea? And what are the possibilities here? In time series modeling, outputs and often also the inputs are real numbers. So not discrete, but continuous numbers, real numbers. So here's an example, the DAX index, and you see an increase, you see noisy looking disturbances, you see some trends, but then also a reversal of the trend and a picking up of the trend. And in fact, financial businesses, the fintech, sometimes called, is a major area where neural networks and similar systems are being used, also for prediction of exchange rates, of stock value, of commodities like energy and so on. Sequence modeling is related. It's about sequences. So here's an example. The input is a sentence, which is a sequence of words, and the output classifies the sentiment of the sentence. So is it a friendly sentence or an aggressive sentence? Is it saying something positive or negative about my company? And this can be used then in marketing, for example, or in other applications. Trying to maybe if you see the trend is that your product gets less positive sentiments, then maybe you need to change something in your product or in the marketing or in the visibility. Another good example is encoder-decoder modeling. So the input is a sentence, for example, a sequence of words in English, and the output is the sentence translated into German. So here the input is a sequence of words, and the output is also a sequence of words. Okay, so I should probably change this last sentence. So here in sequence modeling, inputs and outputs are typically have a discrete nature, not a continuous nature, and they're typically not real numbers. So this was just left over. I will fix that. And yeah, let's start with time series modeling, so-called ARX models, autoregressive models with external inputs. So they are not, it's not the whole story, but it gives you already a very good impression and feel for how this works. So let's y of t, y sub t, be a time series of interest, for example, the DAX. And x of t is another time series that contains information on y sub t, for example, the Dow Jones index. For now, we assume that both are scalars, so they're simple numbers. And the goal is to predict the next value of the time series of y. And a simple assumption is that the following model, y of t, is a function of previous values of y, so yt minus 1 to yt minus t, and is also a function of the previous inputs, so xt minus 1 to xt minus t, and there might be then an additional disturbance we don't know. So this could stand for other inputs or other factors which influence y of t, but it's unknown to us, and often it's simply modeled as a random number. So the simple approach is to model this function from past outputs and past inputs to the next value of the time series by a neural network. So I indicate this here by the W and the V. So it's a neural network with one output, one continuous output, not a discrete output, but a continuous number. And the inputs are simply exactly the same quantities, yt minus 1, yt minus t, xt minus 1, xt minus t. So this would have 2 times large T inputs, and it's really just absolutely normal neural network, multi-layer perceptron with inputs and one output. And if you use the squared error cost function, then you can train it straightforward by backpropagation. And the reason why it's so simple is that all the inputs are known, are assumed known, and also the in the training data, the value for the next time series point is also known. So in this case, it reduces to simple backpropagation. And this model is already quite powerful. Yeah, so the training is simple if all the y's and all the t's are yt and xt are known in the training data. And this model is called an NARX model. So N is for nonlinear because we're using a neural network. Autoregressive means we are looking at previous realizations of the time series, so the yt minus 1 and so on. And X stands for external because we are using also external inputs, the X of t time series. Sometimes it's called also time delay neural networks in this context, or also in the context of sequence modeling. You can also think of it as a convolutional sort of thing because this neural network is sort of shifted across the time series and is applied everywhere with the same function, similar to the idea in convolutional neural networks where the same kernel is applied everywhere in input space. But that's just an interpretation. It doesn't matter. So if we after training, how do we predict? So we just plug in the previous the numbers, previous realizations of the time series from yt minus 1 to yt minus t, and of xt minus 1, xt minus t, and the neural network then gives us an estimate of the value of the time series in the next time step. Also very simple. Sometimes we are not interested in, let's say, the energy consumption of tomorrow, but maybe a few days in the future. So let's say we are interested in tau time steps in the future. And one simple approach is to simply train another neural network to be able to predict tau time steps in the future. So it's exactly the same situation, only that the target is not yt, but it's yt plus tau. So we train it to predict directly tau time steps in the future. And this is quite a popular approach in system simulation. So if you have a complicated plant like a turbine or something, and you want to predict several time steps in the future, then you can directly do a shortcut and predict this value in the future. And this can save you a lot of time because you can replace this forward prediction by an expensive simulation of a differential equation, for example. Of course, it's also possible to just iterate the single-step prediction if you want to do multiple step prediction. But it's not quite so simple because your prediction, you're predicting the mean, but there is some disturbance on the model, this epsilon, which will also affect the model. So doing a simple iteration might sometimes work, but sometimes might also give you a wrong impression of certainty. And there's a lot of literature studying this problem. I just want to give you a feel for what one can do, because one interesting way is simulation. Then we also don't know the xt in the future, and if you want to iterate our prediction model, we also should know xt in the future. So we should have a prediction model for xt as well, so a second model, not just the model for yt, but also for xt. That's why I have this small x up here. And maybe it is sort of deterministic, so this epsilon here is very small disturbance. So then we mostly have to take care of the uncertainty in the prediction of y. And if we assume a particular distribution for this disturbance, for example, a normal or Gaussian distribution with zero mean and some fixed width or covariance, then we can simulate the future based on this model. So this is also the idea behind simulation. And then you cannot just predict one step, you iterate, but you always add the noise to your iteration. And then you do it many times. So by doing it many times, you get an impression of what is the mean in tau steps ahead, but also you get the uncertainty and the variance. So that can be, I'm not sure how much you are familiar with this idea of simulation or Monte Carlo simulation. It's not used too much in this lecture. Maybe I just give you a sort of an intuition, and maybe some of you understand what I'm talking about. So essentially, you use your model and simulate the future by also including the noise model. I'm not going too deep here into this and the details of this. Maybe some of you know what I'm talking about. If you're not familiar with this idea and it's difficult to grasp, that's maybe not too important to understand it at this point. But it's a very powerful concept. And it's also used for simulating plant behavior. There's this concept of a digital twin in industry, which essentially means you should have good ways of simulating your plant or your system or your power plant or your turbines, and use the simulation in a useful way for different solutions. So this is all about time series modeling. And these simple approaches can be quite powerful in some applications. So now we are getting to sequence modeling. And first of all, you have to understand how discrete things are represented. So and the inputs and outputs often stand for words, but they could also stand for other things. So let's assume that xt equals I means that at iteration t, or at a time instant t, x assumes the value I. And I could stand for the identifier of a word. So maybe we have n sub w different words, so maybe 10,000 different words. And I is just an index on the word, and xt equals I means at position t, the input was word number I, with the identifier I. And there's a one-hot encoding. So we add additional inputs, or we represent xt by nw neurons, where neuron I has activity 1 and all others have activity 0. So I'll try to show it here in this picture. So this is one hot encoding, and for one input, so at time index t, we add n sub w input neurons, and the ith one is on, is 1, and the other ones are all inactive or 0. And this encoding is called one-hot encoding. So for each input, we have to spend n sub w neurons. So it's a very common way of encoding a word. And you can also use this for the output neuron, or for the output word. So if you want to predict a word, for example, you can also use a one-hot encoding for the word you want to predict. And then typically you use a softmax representation for the posterior probabilities of these words. And we have just discussed softmax before, and we will encounter it in the future again. So this is the one-hot encoding. Another encoding is called embedding encoding, or sometimes also representation encoding. So let's say for a word I, somebody gives us a vector of maybe high dimensions, maybe 200, 300. So AI, no, this A sub I is just a vector of high dimension, and it's just a vector of real numbers. And in a way, this embedding vector represents, so AI represents word I in some sense of attributes, latent attributes which have been learned, so they don't stand for something I can measure on word I, but they stand for something in an abstract space. I have learned in some application, or somebody else has trained it and made it available for me. So there are these word embedding vectors have been derived from different models, and they are made available, so you can download them and use them in your application. Typically, you fine-tune them for your particular application, but yeah, so they can be trained, they can be download them, and it's maybe a little bit strange in the beginning that this is possible. But why should a word not have attributes? And these attributes are, let's say, stored or computed by somebody. And these embedding encodings can then be used instead of the one-hot index in the input of a neural network, for example. So this is one of these embedding vectors, AI, assuming that xt had the word AI, so then you take the embedding of word I, and this becomes sort of the input to your neural network now. So it's not, you don't have this one hot sort of character, but you have a lot of continuous values as an input to the neural network, so more distributed representation. And you can combine these two ideas. Essentially, it's the same as embedding learning, but it becomes clearer how you adapt these AIs. So we now introduce the matrix capital A, and the ith column in the matrix A contains this vector AI as a column vector. And then you get this situation here on the right. So technically, it's the same as embedding learning. And the embeddings are now here encoded in this connection matrix between the one hot vector here and the representation layer. And now it becomes clear that you can just train this A also by backpropagation if you have an error signal. And so I think this is technically the clearest representation because here it shows you how to do backpropagation. But so the ith column here is the vector I, and if I activate neuron I here, then this one will be multiplied by the column of A here, and it will generate this representation vector here. Yeah, so this is something maybe to get used to a little bit, because we are using this now repeatedly, and it's important to understand this. So let's now look at representation models and language models. So what is a language model? A language model essentially predicts the next word in a sentence out of a vocabulary of NW words based on the T last words. So it's used in natural language processing. And here it looks like a prediction problem, and it is a prediction problem. So we use one hot encoding for YT, for the word we are trying to predict. So YT is the next word we want to predict. And for the word representations, we're using this embedding representations. So we're using the vector AI for the word I. That's in the first step. I mean, so we're using this the C version. So this version here. So we use a one hot encoding of word, which is then mapped to the embedding vector by this matrix I just mentioned. And then then we apply a neural network to these embedding vectors from t minus 1 to t minus t. And I of t minus 1 is the index of the word which was present a time step back, and so on. So we are using these embedding vectors as inputs. We are predicting k outputs, so one for each possible words. We do a softmax, so it's normalized between 0 and 1 and sums to 1. And we interpret this then as a probability that the next word assumes word k, given that we know all the previous words in the sentence. Then all we need is a neural network with many outputs. The inputs are these embedding vectors. Yeah, and here I rephrase or reformulate this. So the word embeddings, it's a very strong idea in deep learning, and they are often pre-trained with a huge corpus, and then you can maybe either use them or fine-tune them for your application. So language models from which these embedding vectors are learned, I just want to mention them. Elmo or BERT. BERT is very new thing. Word2Vec, Glove are typical examples. Yeah, this embedding idea is extremely powerful and one of the cornerstones of modern machine learning. And here's a figure from the literature. So here we have these index representations, so we should have a lot of neurons here. I just show it as this greenish square. Then here we have this mapping from index to embedding. So I always draw it as a matrix. They call it here lookup table. And it's always the same matrix. So that's also the key. Every word in any position has the same representation. So these are the representations here. And there's a hidden layer. And here is the mapping to the many possible words which come next. So this is one hot encoding with a softmax, so we can look at the most likely word, for example, and that's it. No? So it's a more or less simple neural network with many outputs, one for every word. No, so before in the scenario of handwritten digit recognition, we had 10 outputs. Here we have 10,000 outputs. And we have this new idea of an embedding that we map a word to a particular vector by applying the index to this matrix. And then we can inherit sort of information from a pre-trained situation where these embedding vectors were trained on a very large corpus of data. Okay, now we are talking about a recurrent neural network, which I guess maybe almost as important or as important as the idea of convolutional neural networks. And they're particularly powerful for sequence modeling. And they are a way or a simple way of providing something like a memory to a neural network. So let's look at a feed-forward neural network with a time index. So here nothing has really changed. We just indicate already that there's some order in the data. In normal regular training of a neural network, you can change the order of your training data and nothing should change. Maybe a little bit the convergence might be affected, but the order of the data doesn't matter, and often one even first changes the order randomly to avoid that there's some strange pattern in the data which is not helpful. For example, if in the labeling process, maybe first all patterns with the 1 were labeled and then all with the 2 and all with the 3. So that makes the performance typically better if you randomize the order of the presentation of the patterns. But in time series, the order matters. So you cannot, in general, change the order, except for this one special case. So here, essentially, we have the common situation. We have an input, we have a hidden layer, we have an output. So here for t plus 1, here for t plus 2. Here nothing really has changed, so I just want to get you all on the same level. So these are just the same neural network applied to 3 data points. Just labeled them with t plus 1, and t plus 2. So here we are not really exploiting the idea or the concept that this is a time series. So the recurrent neural network is achieved if these hidden units are linked. So there's a link from this layer to this layer. And this is shown over here. So we have, let's say, the regular input to hidden connection with the weight matrix V, then the hidden to output with the vector W, as before. But then a neuron here in the hidden layer also receives input from the activation of the hidden layer from the previous time step. And by doing that, we permit propagation of information in time, or in other words, there's a memory effect because this neuron here is now also affected by the state of the hidden unit, by the hidden units in the time step before. And there's another matrix B here which connects these neurons, and this B is applied everywhere. Since here the sort of the same neural network is copied several times, to show you also very clearly the flow of time, this is sometimes this way of displaying a recurrent neural network is sometimes called unfolding in time, because time is explicit. And now, but as before, the prediction is based on the activity of the hidden layer. And now we're also training B and V and W, all three things. So the notation is quite straightforward. So before, so here nothing changed. The output is a sigmoid or something applied to the activation of the hidden units with some output weight matrix. In this case, I guess I consider a matrix here. And the hidden is a sigmoid applied to the weighted inputs as before, but then we also add a weighted input from the previous hidden layer. So that's this ZT minus 1 also helps to predict ZT, and then everything is trained here. So the next slide shows a recurrent neural network as a recurrent structure. So sometimes people show it in this way. So here you see these feedback connections which indicate the recurrencies. So sometimes this is more appropriate, but I think the display where everything is unfolded in time is clearer and easier to understand what's going on, really. I mean, just drawing all these different mutual connections here is already cluttering the image pretty badly. And then we want to train this construct. So I mean, for training, we have, again, input patterns. So this guy, this guy, this guy, and targets here at the outputs. And we want to optimize everything to get optimal predictions. But now the neural network can exploit also previous information. So, for example, there's a path from previous inputs now to hidden unit here. So it has a nice memory function. And yeah, training, essentially it's backpropagation. No? Just that we have to do backpropagation in this more complicated structure. So the error which is produced here at yt minus 2 is propagated down here to adapt the W and the V's, but it's also propagated through the B layer here, and then maybe affects this layer, affects this layer. So it is still backpropagation, it just becomes more complicated because essentially the error can propagate all the way to the beginning of the time series, and the bookkeeping and becomes more involved and complicated. But technically, and the thing to remember is it's still backpropagation. So you're always backpropagating backwards in time or at the same level. An error here doesn't directly affect the future. And yeah, the common term for this is called backpropagation through time, or BPTT, which is an application of stochastic gradient descent typically to the unfolded network structure. Yeah, in principle, one could backpropagate all the way to the beginning of the time series, but typically you stop after so many time steps in the past. which is called truncation. It's a more practical thing because the gradient often doesn't tell you much about something very long in the past. Yeah, so recurrent neural networks are sometimes difficult to train, not anymore. In the modern times, the algorithms and the hardware and the software which is available makes it not too difficult to train, but when they were invented in the 90s, they were quite difficult to train. And in the 90s, it was not even clear if backpropagation through time and recurrent neural networks were really powerful and really did useful things, um, at least outside of the insider community of experts. There was quite some skepticism if this really works. And then for me, an eye-opener were the echo state neural networks, which gave pretty good results on a number of interesting applications. Um, yeah, they're called echo state networks, uh, in their special case, or the more general term is reservoir computing, and another line of research is called liquid state machines. Just that you have heard the terms. And the architecture is very simple. So we have, maybe let's look at our familiar picture. So we have a recurrent neural network, and we are just initializing the V's and the B's in a more or less intelligent way, but pretty randomly. And the only thing we are training is this W vector over here. So we never change the B's and the V's. And this seems like an absolutely crazy idea, but it works surprisingly well. I mean, you need to have a sufficiently large number of hidden units, but it seems these dynamics which are forming here, which are building up, are for many cases rich enough so that for a particular application you only have to adapt the W's. And this is shown over here. So here are the units in the hidden layer. They're all connected. So this is again this not unfolded in time representation. We have an input or several inputs which are driving these neurons here, and then we have one or several outputs where we only train the connection weight from the hidden units to the output, but we never train anything here or here. So that's pretty amazing that this works, but it works surprisingly well. And for me, it was telling me that, oh, these recurrent neural networks seem to have something and they seem to work. And that was when I got interested again. So that was, I don't know, around 2000, 2005, when these were popular or were invented. So just as a concept of proof that this really works. Yeah, so the RNNs are doing prediction based on the input. And in contrast to when we discussed about time series, the values of the time series also affected future predictions. That is typically not so much the case here. So typically you predict from a clear input X to Y, um, and the feedback from actual measurements Y uh, can also be done, but it's a little bit difficult with recurrent neural networks. But this is sort of the domain where hidden Markov models, Kalman filters, and stochastic state space models are applicable. And there are also generalizations of recurrent neural networks to these type of problems. So the Ys are used for training, of course, but often not in prediction. The prediction only occurs based on current and past inputs. And partially to solve this problem, people invented bidirectional RNNs, so it's easier to see what's going on in the picture. So here are the inputs, here are the outputs. So here are two sets of recurrent neural networks of latent of hidden states neural networks, and one is doing the normal feed-forward recurrent neural network, but then there's also one which is going backward in time. So if you have to work with a sequence which is completely available, like a sentence, this is a good idea because you have the whole sentence and you can go forward and backward in time. And so you get one representation for the forward path and one representation for the backward path. And based on both, you then predict the output. So this helps you because you don't just transport information forward in time, but also backward in time. And so the prediction at a certain instance here can use information from the past and from the future. And they're called bidirectional recurrent neural networks. And here, so the hidden layer is divided up into a forward vector and a backward vector, and the forward one uses information from the previous time instant and the backward one from the future time instance. And then you are training all these V's and B's in the regular way. And they are quite powerful and used a lot in language type of problems. So this recurrent neural networks work reasonably well, but they became really powerful when people invented LSTMs. So yeah, it stands for long short-term memory, and they were invented by Sepp Hochreiter and in collaboration with Jürgen Schmidhuber. So I showed the picture, I think, in the lecture of deep learning. So RNNs have a memory, but they have difficulties remembering something far in the past, and this can be attributed to the so-called vanishing gradient problem. So I mentioned that briefly in these type of neural networks. If you have an error signal and you want to backpropagate it considerably distance in the past, then this gradient sort of becomes smaller and smaller, just for numerical reasons. It's still the correct gradient, just the influence becomes smaller and smaller, and this can be a problem in some applications which require a long memory. Solutions are the long short-term memory, LSTM, or a different variant is the gated recurrent units, the GRUs. And they were invented by a group in Germany, Schmidhuber and Hochreiter. So they are, I have to warn you a little bit, they are a little bit complicated, difficult to understand, but I'm trying my best to explain how they work. So let's first look at a simple feed-forward structure, so no recurrency yet, and look at this particular feed-forward network. So here's the input X. We multiply it by a weight matrix V. We apply the sigmoid, and we get a hidden representation S of t. And then, which is novel, there's another transformation from S of t with a tan-h nonlinearity to a vector zt, so another latent vector here. And then the output is predicted based on an application of a weight matrix to this z of t, and we apply another sigmoid. So the transfer function of the hidden neuron is a bit strange because it's essentially it's a tan-h applied on a sigmoid, and these things have names also. So S of t is called S sub t is called the cell state vector. Z of t is the output vector. So it's the output of the LSTM unit and not the neural network. And these are all vectors, so we have, the dimension is h. So we have, or if you draw them as individual neurons, we have h of these LSTM units in the network. But this is already captured here in this vector notation. So this is a little bit strange maybe, or unusual, but it's a simple feed-forward system. And the next complexity we are adding are these so-called gate functions, which are between 0 and 1. So we multiply here this expression, the sigmoid applied to the v times xt, pointwise, so element-wise, by a gate vector. So each output here can be multiplied by a number between 0 and 1, and they can all be different. So the st, which is a cell state vector, is now the sigmoid applied to v applied to xt, but then also pointwise multiplied by this gating output, g of t. And we do the same thing also here for the z of t. So we have another gating vector which pointwise multiplies the output of the tan h of s of t by another gating vector, again element-wise. The symbol is also called Hadamard product. And the output then is calculated as before. And now what are these gating factors here, these gating functions? So they are also functions of the inputs with another weight matrix. So the same is true for g of t and for q of t. They have different weight matrices and are looking at the inputs. So these gates have a longer history in neural computation, and they're used in the so-called mixture of experts. So it allows you to switch between different modes of operation. That's maybe the way to look at that. So now we introduced, on this slide, we introduced the input and output gates. And now we make everything recurrent. So the input to the ST layer is recurrent. So it looks at previous outputs of the Z layer and gets connections from there. And also the input and output gate now have a recurrent structure. They also look at a matrix applied to the previous Z vector. And they have exactly, also again, different matrices they are learning here. So that's almost it. The final addition is that this ST layer also has its own feedback direction, not just from Z, but also, so S of t is a function of its last vectorial representation, st minus 1, with another gate. So that's the third gate, the so-called forget gate, which has a similar structure as the other gates. And it's also a pointwise multiplication. Here let me first show you how it's sometimes shown in practice. And it looks quite complicated, and it's also quite complicated, and it's not necessarily easy to understand why it works. So here's the y is the output, here's the input. We have the first nonlinearity here. Here's the input gate, which is a pointwise multiplication. The input gate also has recurrent and input connections. Um, Here's the cell, which has a recurrency, which has another gate, a forget gate. Here's another nonlinearity. And then there's another output gate, this O here, which also has inputs and from the recurrent connection. And then finally we have the outputs here. So, and this is just one neuron, and we have many of them. One hidden neuron. And the interesting thing is that they work very well, and in particular for that person, for that purpose, that it provides a long-term memory. If desired, it's sort of controlled by the gate, so the gate can control if a memory is needs to stored for a long time or can be forgotten quickly. So here I gave a basic idea. At time T, a newspaper announces that the Siemens stock is labeled as buy. The information will influence the development of the stock in the next days. A standard RNN will not remember this information for very long. One solution is to define an extra input to present that fact that is on as long as buy is valid, but it is handcrafted and does not exploit the flexibility of learning of recurrent neural networks. And a flexible construct which can hold the information is a long short-term memory LSTM block. And it has been very successful in many applications, for example, reading handwritten text, in natural language processing, in machine translation, and the only sort of new development which sometimes replaces LSTMs are these the attention mechanisms we will discuss shortly. Again, here's the picture of an LSTM. I guess this is supposed to be a whole block, so these are all vectors. Yeah, okay, but you can also take them apart as neurons, whatever. And you can look at them as particular neurons with particular connection weights. Yeah, so on the Wikipedia it says LSTM achieved the best known results in unsegmented connected handwritten writing recognition, and in 2009 won the ICDAR handwriting competition. LSTM networks have also been used for automatic speech recognition and were a major component of a network that in 2013 achieved a record 17.7% phoneme error rate at the basic timid natural speech data set. Other applications here are robot control, time series prediction, speech recognition, rhythm learning, music composition, grammar learning, handwriting recognition, human action recognition, protein homology detection. So they are really a hit and were really a major breakthrough. So now, we are looking at a particular encoder-decoder application. So you might be curious of how machine translation works, which you might be using. For example, if you're using Google Translate. And these encoder-decoder architectures have, I think, replaced almost all other approaches, although I think some of them use convolutional approaches, but this is a major breakthrough. It's called neural machine translation, and we are using word embeddings with a rank of, let's say, 1,000 and 1,000 hidden units per layer. So here is a typical architecture. So you want to put in the sentence, I am a student, and the neural network should produce the sentence in French, Je suis étudiant, and then also know that here's a stop, I can stop. And this is not at all trivial, particularly if you're using languages with a very different character, English to Chinese, something. And this is a powerful architecture for that. So you see here a system unfolded in time. So the input is the sentence. And you're using embedding encoding, so you're presenting the latent vector or the embedding of I, of M, of a student, and it's 1000 dimensional. And you might have pre-trained it somewhere, or somebody pre-trained it for you. So you have 1000 inputs here. Then you have also on the order of 1000 LSTM units. And you see here the architecture of the LSTM network. And then you're using 2 layers of them. So here's another layer of LSTMs. And adding the second layer improved performance. But you notice that there is no instantaneous output. So you don't train it on an immediate output for each time slice here. You're just training this, and then at the end of the sentence, you have a representation or 2 representation vectors. The activation of the last state here, when the sentence ends. And that's why this is called an encoder. It encodes the sequence of words here into these vectors, which are then represented here. And then these representations form from the input to the first layer of the decoder, which produces the sentence in French in this case. It's the same architecture with 1000 LSTMs in these 2 layers each. And then, but now you have outputs. So you have links from this layer to the output layer, and this is one hot encoding. So you have maybe 10,000 output neurons here, and maybe the highest activation here was for the word index for je. And then in the next time step, it produced suis, and then in the next time step, it produced étudiant, and then it produced end of sentence. So that's and this error here needs to be propagated as before through the whole recurrent unfolded system here. So that's how the error signal also changes the blue layers, because the error is backpropagated in time also to the blue layers. So that's almost it. There's one more thing. These decoders also have inputs. So when here it was decided that je is the most promising prediction here, then this prediction also becomes an input for the next time instance. And if this was predicting suis, then it's also the input here to this to this layer, and so on. And since now you get a dependency between the different decodings, you're trying many of them, or you're trying to find the maximum likely sequence. So it's not necessarily a greedy approach, which I just described, where you take the maximum likely word, you put it in here, take the maximum likely word here. So you do a little bit of a tree search to find the maybe most likely sequence of a decoded sentence. And that your own prediction becomes the input, sometimes called teacher forcing in the literature. So in the encoder, there's no output, but several layers of recurrent units. And the inputs are the latent embeddings of the words. Then the encoding vector is the last of the states at the end of the hidden units. So exactly here, this is the encoding, and then the encoding becomes decoded by the decoder. So the initial latest state of the decoder are the encoder vectors, and in its simplest form, the we use this equation here. So the representation of the latest date is b of z t minus 1 plus a of y t minus 1, because the prediction becomes the input again. So this is the later representation of the predicted word. So so if j is predicted as the most likely word here, then we're inputting the latent representation of j in this place. And this is shown in these equations. So I think the rest we already talked about. And of course, it has been exploding, this type of applications. It's the neural machine translation achieves state-of-the-art performance in large-scale translation tasks, such as from English to French. And NMTs have the ability to generalize well to very long word sequences. And the model does not have to explicitly store gigantic phrase tables and language models, as in the case of standard machine translation. And NMT also has a small memory footprint, so it doesn't require much storage. And implementing the NTM decoders is easier, unlike the highly intricate decoders in standard MT. And so this is another example where you can use deep neural networks on the raw data, so you don't have to do some fancy feature engineering before. And this made sort of machine translation also accessible to people who are not so much experts in natural language processing in general. So this is maybe a very important intermediate step to understand how this encoder decoder architecture works, and there are many generalizations to this, not just in language modeling but also in other applications. So now we are coming to another interesting methodology. I already said that recurrent neural networks are partially replaced by attention mechanisms. The concept of attention has gained popularity recently in training neural networks, allowing models to learn alignments between different modalities, for example, between image objects, agent action in dynamic control problems, between speech frames and text in the speech recognition tasks, or between visual features in a picture and its text description in the image caption generation task. Attention has successfully been applied to jointly translate and align words. Attention-based neural machine translation are superior to non-attentional ones in many cases. For example, translating names and handling long sentences. And here's one paper we are following from the group of Chris Manning. Effective approaches to attention-based neural machine translation. The initial paper is here from Benjo's team, Badanao, Cho, and Benjo, neural machine translation by jointly learning to align and translate. So the next figure shows the overall architecture. and the attention layer sits on top of the normal encoder-decoder network, and it calculates new activations in the gray boxes. So we are seeing here the recurrent neural network from before, but on top we have another layer which is called attention layer, and this attention layer calculates these representations in these gray boxes, and from the gray boxes we then predict the decoded words, and then we also use this teacher forcing that the predicted word becomes the input to the network in the next instance. So the explanation is as follows. So let's Z of t be a hidden state vector of interest in the decoder. Yeah, so on the right side. Sometimes it's also called a query. Then let's C sub t be the source side context vector, which we show in a moment how this is calculated. Then the attentional hidden state is a combination of the Z of t, which was calculated in the regular manner, and we have a weight vector on top of that. But we also get input from this context vector C sub t with its own weight matrix. And if this attention is not necessary, we can just set this d to 0 and we get more or less our old model back. Often the turn h is used instead of the sig. So you can also think of that these zt and ct are appended, and then you're learning a joint matrix consisting of v and d. And then, so z of t, this z tilde of t is then, the second to last layer, and then the last layer decides which word is predicted with what score. So now this z bar of s is any activation vector in the encoder, so on the left side. And typically we are working with the top layer. This is called the key. Then the next thing is that one calculates an alignment. So this is just a number between t and s. Sometimes written a line of zt, so the one in the decoder, and the bar zs in the encoder. And a typical equation is here. So it's the exponent of the score and then normalized, so it sums to 1 and it's positive, or it's not negative, sums to 1. And this score here in the exponent is some similarity measure. And a simple one is simply the inner product of these two vectors. So this alignment essentially calculates how similar t and s are based on these vectors. So the one I'm currently interested in, the z sub t, and we calculate this with respect to any of the representation vectors in the encoder. And then the context vector, which we already encountered here, is then simply a weighted sum of the representations in the encoder, weighted by this alignment score. So this alignment score will give a larger weight to a latent vector which is closer to the representation of the current time step. So it sort of looks at similar words in the encoder, uh, and it's sort of time invariant. So if the word was far back or a very different location in the input space, then if it has a very similar representation, then it will get a high score here, and it will have a large influence on the prediction of the output. So this is, for example, important if the word order changes from one language to the other, then this alignment, and can find the word in the encoder which is relevant for the decoder. So this is shown over here. So here the ZTs, the S's with a bar in the encoder. This is the ZT we are currently interested in to predict the next word. We are calculating this alignment score between Z of t, so the latent vector here, and all the instances in the encoder. This gives us sort of factors, weighting factors. Then we average all these latent representations here in the encoder, weighted by a sub t. This gives us the context vector, and then the context vector plus this zt vector are inputs to this z tilde vector, which is then the layer which predicts the word in the last layer. Yeah, so it is a little bit difficult or complicated, and it takes a little bit while to get an intuition why this works. But the idea is essentially that if there's a vector here and the word vector which is not in the same position in the input sequence, then this attention mechanism can find it. So this was the global attention model. There's also something called a local attention model, where essentially we first estimate the location of the word in the encoder, which is relevant for the decoder. Because this global one is expensive and becomes difficult to handle in longer input sequences. So essentially they multiply this align here with an exponent which tells you how close the word in the encoder is based on some predicted position of this word. So you're focusing on some place in the input sequence, and you give it like this Gaussian shape. And here's how it is. I mean, it's another small neural network which predicts the position in input space, and that seems to sometimes improve performance. So this is shown over here. We also have not everything as before, but we also have this aligned position vector, which gives another weighting to the different input latent representations. I'm not sure if I say ignore the dashed lines. Anyway, so this was the architecture I've shown before. Yeah, and then people discovered that this idea of attention also works not just in encoder decoder frameworks, but also for a single whatever word classification or sentence classification, where you only have one sequence you are paying attention to. And it's the same idea, And it might be easier to see when I show you the pictures which belong to these equations, because we are doing a comparison here. So let's think about word sequences, and we do a simple feed-forward neural network. So that's this architecture over here. So this might be somewhere in the hidden layers. No? It might, it's not necessarily the input or output layer. But in a simple feed-forward architecture, everything is feed-forward, so there's no mutual influence. Every word is predicted on its own. Of course, there's weight sharing, so all these neural networks are essentially the same. But there's no mutual influence between the prediction of the words. So this is the feed-forward neural network. Then the other extreme is using a fully connected architecture, which is not really used in practice, but that's shown over here. So every hidden layer influences every other hidden layer and the next layer, and there's no structure in these connections. So that's not being used at all. It overfits. So the next one is convolutional architecture, which looks fully connected, but it has this symmetry constraints, this sharing of parameters. So all the red connections here are the same, and all the blue ones are the same. And if we would have a longer sequence, then you would even see more of this symmetry of this parameter sharing. And this can give you good results also in natural language processing and some of the leading translation systems or sequence labeling architectures in natural language processing have this architecture. So it's not bad, also not for sequence. So then the next one is the recurrent architecture, which is shown over here. So we start with our normal feed-forward architecture, and then we, as we discussed, we feed latent to latent and latent to latent, and this can be LSTM or this could be a normal, just a layer-to-layer connection. And you see that information between neighboring inputs is shared, in particular in the forward direction. And if you want to have sharing in the forward and the backward direction, then you use these bidirectional architectures where information can flow in either direction. And then the last one is self-attention. So we have, again, a feed-forward structure, which is this green vectors with weight connections matrix V. But then this gets additional inputs, and essentially we take the activation of all the all the neurons in the last layer, and first we form a weighted average. But these weighted averages are all different and are weighted by these alignment scores, or these which are individual for each of these layers. But they are essentially weighted sums of these layers, just they are all different weighted sums based on the similarity between the latent representations. And then we learn another matrix here from these attention layers to the prediction. So maybe in this figure you can see nicely the common things and the different things between the different architectures. So in conclusion, sequential models find many applications in natural language processing, including machine translation. And so in sequential modeling, recurrent neural networks or LSTMs are very powerful, and increasingly also attention mechanisms are being used. Attention mechanisms are also the basis for state-of-the-art machine translation, like the transformer architecture, and I cover them in the appendix, so if you're interested, you can take a peek and then maybe look at the literature. Transformers are even more complicated, so I don't want to discuss them in this lecture. And they even remove the recurrency in the encoder and decoder. And the key phrase they're using is attention is all you need. You don't need recurrency, or you don't need convolutional layers, only attention. And yeah, transformers work very well. They're quite complicated, but they give very good performance in machine translation. And another application is context-sensitive embedding models, the so-called BERT model, which gives you excellent word representation. So these embeddings I was talking about, and these embeddings are even context dependent. So you're not looking them up in a dictionary. You're calculating them using the BERT model. Okay, so this was all I wanted to tell you about time series and sequence models. So sequence models, yeah, I think recurrent neural networks are still easy to grasp, but the LSTM and attention is a little bit complicated. But this brings you up to the current research, and you have an understanding of what is going on in research in sequence modeling. Thank you very much for your attention.